Okay, hello everyone. Welcome back. Um, this is going to be our third part of the um, AP Physics C magnetism unit, and I'm going to walk you guys through two FRQs. So let's start with our first one, which is a solenoid question. A solenoid is used to generate a magnetic field. The solenoid has an inner radius A, length L, and N total turns of wire. A power supply not shown is connected to the solenoid and generates current I, as shown in the figure on the left above. The x-axis runs along the axis of the solenoid. Point P is in the middle of the solenoid at the origin of the XYZ coordinate system, as shown in the cutaway on the right above. Assume L is much greater than A. So first, we're going to select the direction of the current of the magnetic field at point P. And so using our right-hand rule for coils and loops of wire, we'll see that the magnetic field is going to be in the positive x direction because the magnetic field will go with the direction of current. So our justification will be the right-hand rule for solenoids. When the fingers curl with the current, the thumb points in the positive x direction. Now let's move on to the next question. On the cutaway view below, clearly draw an Amperian loop that can be used to determine the magnetic field at point P at the center of the solenoid. And then part 2, use Ampere's law to derive an expression for the magnetic field at point P. Express your answer in terms of I, L, N, A, and physical constants as appropriate. So let's get right on with I. We know that an Amperian loop is going to be a rectangle about the center, and conceptually, the only significant part of this rectangle will be the part along the axis of the solenoid. And so for part 2, using Ampere's law to derive an expression for the magnetic field strength at point P, we can use our formula from the formula sheet. The B field of a solenoid is equal to mu naught Ni, where N is the number of loops divided by the length, and we can get our expression. The B field of the solenoid is equal to mu naught large Ni over L. Okay, so moving on to the next part, which is a graphing question. Graphs are going to be pretty common on this part on any magnetism FRQ. So it says some physics students conduct an experiment to determine the resistance R sub S of a solenoid with radius A equals 0.015 meters, total turns N equals 100, and total length 0.4 meters. The students connect the solenoid to a variable power supply. A magnetic field sensor is used to determine the magnetic field strength along the central axis at the center of the solenoid. The plot of the magnetic field strength B as a function of the EMF E of the power supply is shown below. So on the graph above, we're supposed to draw best fit. We're supposed to use a straight line to determine the resistance R sub S of the solenoid used in the experiment. And then we have some experimental questions that we'll get on to answering. For part C of the C1, drawing the line of best fit is incredibly easy. I drew mine through the origin. And then to use a straight line to determine the resistance R sub S of the solenoid, we'll have to construct an equation now. So we know that V over R sub S is going to be equal to I, the current. So we're going to use the B field equation that we saw earlier, and we're going to substitute V over R sub S in for I. We're going to get B sub S is equal to mu naught N V over R sub SL. And we want the form y equals mx. And so we divide it into this, and we calculate the slope to be 3.85 times 10 to the negative 5 Teslas. A common mistake here will be that an individual plugs in the Teslas as 2.5 instead of 2.5 times 10 to the negative 4. So that's something to watch out for. And then we just have to isolate for the resistance, and we get 8.16 ohms. And there's a large range depending on how you calculate the slope. And so now going on to question D, one of the students notes that the horizontal component of the magnetic field of the Earth is 2.5 times 10 to the negative 5 Teslas. Is there evidence from the graph that the horizontal orientation of the solenoid affects the measured values for B? So there are two different correct answers here. The first one is no. There's no y-intercept present, so the Earth has no effect on the solenoid. Now, if you were to draw graph with a y-intercept, you could say yes, and you said yes, a y-intercept is present, so the Earth has an effect on the solenoid. But moving on to the second part, will the horizontal orientation of the solenoid affect the calculated value for R sub s? The answer is no, regardless of what you put for D1, because even if the Earth interacted with the experiment calculating the resistance of the solenoid relies solely on the slope and not the y-intercept. And that's going to be the end of our first question. So moving on to our second question, this is a mass spectrometer question, and it's another frequent one that we'll see if there's a magnetism FRQ. So it says two plates are set up with a potential difference V between them. A small sphere of mass M and charge minus E is placed at the left-hand plate, which has a negative charge and is allowed to accelerate across the space between the plates and pass through a small opening. After passing through the small opening, the sphere enters a region in which there is a uniform magnetic field of magnitude B directed into the page, as shown above. Ignore gravitational effects. Express all algebraic answers in terms of V, M, E, B, and fundamental constants as appropriate. So the first thing that we should be thinking is mass spectrometer. We're going to be in centripetal motion of some sort. So what is the initial direction of the force on the sphere as it enters the magnetic field? It's going to be towards the bottom of the page. And so here we're going to be using the left-hand rule, where our left hand, the thumb will be pointing to the right, our fingers will be pointing into the page, and the force will be towards the bottom of the page. And so the sphere, so then to describe the path taken by the sphere after it enters the magnetic field, the sphere will move in circular motion to the bottom of the page is an appropriate answer. Next, two plates are set up with a potential difference V between them. A small sphere has a mass of M and a charge of negative E and is placed at the left-hand plate, which has a negative charge and is allowed to accelerate across the space between the plates and pass through a small opening. After passing through the small opening, the sphere enters a region in which there is a uniform magnetic field of magnitude B directed into the page as shown above. Ignore gravitational effects, express all answers in terms of V, M, E, B, and fundamental constants. So first we're going to derive an expression for the speed of the sphere as it passes through the small opening. And for this we'll use conservation of energy. So it's going to be converted in from kinetic energy into potential energy. And so we'll see we have our equations here. 0.1/2 mv squared is equal to negative qv, and we simply isolate for v and get this expression above. Now to do part C, derive an expression for the radius of the path taken by the sphere as it moves through the small opening. We will start with a slightly different setup, which is that the force is going to be equal to qvb, where the force is mv squared over r. And then we'll isolate r because we want the radius. And then we're not allowed to use little v, which is velocity. So we'll sub in from our last part, our velocity expression in terms of the v, which is the potential difference, e and m. And so we'll get that r is equal to the square root of 2mv over e b squared. And so that's just substitution and sort of connecting everything together. For the next part, I'm not going to read this all because we're running out of time, but we have an experiment where the beam of electrons is going to be accelerated across differing potential differences, and as a result, the magnetic field will change. And so we have a bunch of tasks below. So the first one is indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the charge to mass ratio of an electron. So we should go back to the previous question, whose answer was r is equal to the square root of 2mv over eb squared. We'll square both sides, and then we'll isolate b squared as our y component, which is our vertical axis, and the voltage v as our horizontal axis. And so now we can sort of see that the quantities that we'll have to graph are potential difference against magnetic field squared. And so I have all of those values imported into the table, which will then be graphed. And so we have the magnetic field squared graphed against potential difference, and we have a line of best fit across it. And so important things to note, our units are the magnetic field squared and the potential difference, and we have them labeled, as well as we have all of the numbers labeled. And so for the final part of this question, we want to use the line of best fit to determine the mass to charge ratio. So we know the slope is going to be two quantities minus another two quantities. And so we'll plug this in. So we'll do 14 minus 9.2 over 120 minus 80 is equal to 0.12 Teslas times 10 to the negative 3 squared per volt. And so then we'll plug this quantity into the slope is times the radius squared over 2 is equal to the mass per charge ratio. And eventually we will get 6.0 times 10 to the negative 12 is the mass to charge ratio. And that's going to be the end of our FRQ. So thank you everyone for watching this series on magnetism, and good luck on the AP.